Okay, hold on. All right, so section 5.3 entitled the binomial distribution. When we get done with this section, we will be able to compute exact probabilities for X successes and N trials of a binomial experiment. We're also going to discover what a binomial experiment is versus what is not. We'll be able to compute the mean and the variance and standard deviation for this discrete distribution, the binomial probability distribution. And you might want to get your calculator handy, as the TI-84 has the functions that are going to enable us to compute binomial probabilities. The TI-84 calculator supplants having to use tables in our appendix of our textbook. Is there anybody on board here that does not have a TI-84 calculator? Anybody? So is it a fair assumption to say that we all have access to a TI-84 calculator? All right. All right, ladies and gentlemen, let's open this up by first of all defining what a binomial experiment is. A binomial experiment is a probability experiment that satisfies the following four requirements. Number one, there are a fixed number of trials in the experiment. So whatever the experiment is, you cannot have like an infinite number of trials. There has to be a fixed number of trials, like 10 trials or 100 trials or 500 trials. Okay, there has to be a fixed number of trials. Number two, to be a binomial experiment, each trial has two possible outcomes, which are called success and failure. Any trial, ladies and gentlemen, that has two possible outcomes is called a Bernoulli trial. Okay, a Bernoulli trial. So all binomial experiments have two outcomes per each trial. An example would be, suppose that we, at any random time, determine if a light bulb is on or off. So when we check, the light bulb will either be in one of two states, either on or off. That's called a Bernoulli trial. All right. Another example would be, a Bernoulli trial would be rolling a die. I could either roll an odd face or I could roll a what? An even face. So there's two possible outcomes for that particular experiment. We would call that a Bernoulli trial, and therefore a binomial experiment, provided that there are a fixed number of trials in the experiment. Each trial has two possible outcomes. Number three requirement, the outcomes of the trials are independent from each other. So when I flip a coin, there's two possible outcomes. I could either flip a head or a tail. And do you agree, if I flip this coin 20 times, that flip number 15 does not know or care what flips 1 through 14 yielded? Do you agree?
Yep.
Because of that, we say a coin is memoryless. All right. Those trials of flipping that coin are said to be independent trials of each other, because what happens on any previous trial of the flip of the coin in no way, shape, or form affects the probability of any subsequent flips of that coin. Okay, those are called independent trials. Would these be independent trials if I reach into a deck of cards and pull out a card and then keep the card out of the deck and then reach in a second time and pull out another card? Are those considered independent trials?
It'd be dependent.
Yeah, that's right, because that's an experiment without replacement. And what card I draw on the first trial because I'm keeping it out of the deck, okay, does, okay, affect the probability of what card I would draw on the second trial. Now, if I drew a card from a deck and put it back into the deck and reshuffled the deck and then pulled out another card out of the deck, then those two trials would be independent of one another, because that's an experiment with replacement. Okay. All right. The fourth requirement for an experiment to qualify as being a binomial experiment is that the probability of a success or a failure must be the same every trial. Okay, must be the same every trial. In other words, let me give you an example. Suppose when I have a biased coin, suppose the probability of tossing a head on my coin is like 70%. Okay, so if I toss that coin for 20 times, 20 trials, then the probability of tossing a head on each of those 20 trials must remain the same. Namely, it must be 70%. Okay. So again, the probabilities of having a success on a trial of a binomial experiment or a failure must remain the same trial to trial to trial to trial. Those probabilities cannot change. In other words, I mean, like if I have a coin, if the probability of tossing a head on the first toss is like 70%, and the probability of tossing a head on the second toss of that coin is 50%, that is not considered to be a valid binomial experiment, because the probability of a success or failure is changing trial to trial. Okay, that cannot happen with a binomial experiment. So those are the four requirements in order for an experiment to be classified as a binomial experiment. If one of those is not satisfied, just one of them is not satisfied, then we do not have a binomial experiment. Now, this word success, ladies and gentlemen, is a little misleading, because when we think of, the probability of experiencing a success in an experiment, we think that that's a good thing. That doesn't necessarily have to be always a good thing. A success could be that we randomly select a battery from, let's say, 100,000 batteries, brand new batteries, and that battery being no good. That could be considered to be a success based on how we define what a success and a failure is. So again, don't think a success is always a good thing. All right. It just depends on how we define, or what we define to be a success versus a failure. Most of the times, however, the success usually is a good thing, but it doesn't always have to be. All right. So if I have a coin, let's say a fair coin, and I define the random variable x to be equal to, if I toss this coin, let's say 20 times, if I define random variable x to be equal to the number of heads I toss in 20 trials, and again, there's 2 outcomes per trial, all right, because I'm interested in a heads occurring on any toss, I would call that a success. And so therefore, what would be defined to be a failure for this experiment? If I'm calling tossing a head a success, then a failure would be that I toss a what? I toss a tail. Okay. But I could just as well turn it around. I could say, suppose I define a success to be that I toss a tail on a coin. Then a failure would be that I toss a head. Again, it depends on how we define what a success and failure is for a binomial experiment in any trial. All right. The outcomes of a binomial experiment and the corresponding probabilities of these outcomes comprise what is known as a binomial probability distribution. And we seen that a couple of days ago when we defined what a discrete distribution was. Well, actually, that was last week. What a discrete distribution was, it had to be a finite discrete listing of outcomes of an experiment coupled with their associated probabilities. And of course, the probabilities can never be, any number outside of the range of 0 to 1 inclusive. And we discovered that the sum of the probabilities of any valid discrete probability distribution must always sum up to 1. That's also true for a binomial probability distribution. Whoops. Okay. All right, so let's try a couple of these. Which of the following experiments are considered to be binomial experiments? Ladies and gentlemen, I'm going to call this classwork number 1 right here. Classwork number 1. Now, hold on a second. I'm going to help you out here. What I'm going to go do here is I'm going to use my snipping tool. And I'm going to snip these 4 requirements for an experiment to be a binomial experiment. I'm going to snip that, and I'm going to go to here, and then I'm going to bring this up. And I'll get it out of your way here, hopefully. There you go. All right, classwork number 1. For each of these problems, 1 through 4, I want you to determine which ones are binomial experiments, which ones satisfy all 4 requirements here. Go ahead and do that. That'll be classwork number 1. All right, ladies and gentlemen, let's take a look at these now. Remember, to be a binomial experiment, all four of these criteria need to be satisfied here. Okay. So how about number one, rolling a die 20 times and recording the outcome each time? Is that considered to be a binomial experiment or not? Anybody have any thoughts on this?
No,
Why not?
because there's more than two outcomes.
That's right. Any trial could yield more than two outcomes. There's 6 possible outcomes when you roll a die. For that reason, these are not Bernoulli trials, and it's not a binomial experiment. Okay. So that's the reason why. Number two, rolling a die 20 times and recording whether the outcome was even or not. And of course, if it's not even, it must have been an odd roll. Is that a binomial experiment? Is that a binomial experiment? Well,
Yes,
yeah, let's check it out. Number one, are there a fixed number of trials for this experiment? The answer is yes. We're rolling the die 20 times. Number two, are there 2 possible outcomes on any trial? Well, there are, based on how we define the outcomes. We could roll either an even face or an odd face. There's 2 possible outcomes. That checks out. Number 3 requirement. The outcomes of the trials are independent from each other. That certainly is the case. When you roll a die, doesn't matter if you roll a die 10 times or 100,000 times. Previous rolls are not recorded by the die. The die doesn't remember what happened on any previous rolls. We say a die is memoryless. Okay, so that checks out. Requirement number 4, the probability of success is the same on every trial. Well, defining a success for this experiment to be that we roll an even face, that probability of occurrence on any given trial is satisfied if we roll a 2 or a 4 or a 6. So that would be 3 out of 6 chances, or 1/2 or 0.5 or 50% chance of rolling an even face or having a success on any given trial of rolling this die. And because that 50% probability is the same whether we roll the die on the first roll or the 20th roll, the probability of having a success never changes. And so requirement number 4 is also satisfied. So this would be an example of a binomial experiment. Okay, so this one is good. How about number 3? Is number 3 a binomial experiment? Anybody?
No,
Why not?
it's without replacement, so the outcomes are dependent.
That's right. Now look at, there are a fixed number of trials of this experiment because we're drawing 5 cards. Number 2, are there 2 possible outcomes when we draw a card from a deck? Yeah, there are. It's either a face card or it is not a face card. So requirements 1 and 2 check out. Requirement 3, the outcomes of the trial are independent from each other. No good. They are not. Not in this case, because when we pull a card out of the deck, ladies, I'm going to note whether it's a face card or not. We keep that card out of the deck. By doing that, by not replacing the card back in the deck for subsequent draws or trials, the probability of what cards we pull out on any later trials is affected by what we pulled out on the first trial. So the outcomes of the trial are not independent from each other, they're dependent. And therefore, because they're dependent trials, the probability of a success will not be the same for every trial. The probability is constantly changing because you're constantly leaving more and more cards out of the deck, which reduces the total number of cards to draw from, which ultimately affects probabilities of what happens on later draws. This is not a binomial experiment. Now, number 4, suppose we draw 5 cards from a deck one at a time, recording whether each card is red or black, then reshuffling the card back into the deck before drawing the next card. This is now an experiment with replacement. And because of that, I think this one will be a binomial experiment. Let's check all 4 requirements quickly. Are there a fixed number of trials? Yes. We're selecting 5 cards. Each trial has 2 possible outcomes. Yes. It is either a red or a black card. Number 3, the outcomes of the trials are independent from each other. Yes, because this is an experiment with replacement. We're replacing the card back into the deck before we select another card. Number 4, because it's an experiment with replacement, will the probability of a success, however we define a success to be, whether we draw a red card or a black card, will that probability remain the same for every trial? And the answer is absolutely yes, because it's an experiment with replacement. So this is a valid binomial probability distribution. Any questions how we determine whether or not an experiment is binomial? Okay, so we good on that? These 4 requirements here? Okay. Let me erase this here. Okay, now we can move on here. Get rid of that there. All right, ladies and gentlemen, let's now begin to introduce ourselves to the binomial probability distribution function. The outcomes of a binomial experiment and the corresponding probabilities of those outcomes comprise what is known as a binomial probability distribution. A discrete random variable x has a binomial distribution if its values equals the number of successes in a binomial experiment. Let's read that again, that's important. A discrete random variable x has a binomial distribution if its values equals the number of successes in a binomial experiment. So it's always equal to the number of successes in a binomial experiment. All right. When talking about binomial distributions, n refers to the number of trials. Lowercase p is the probability of a success on any given trial. Q is called the complementary probability. It's 1 minus p. So Q must be equal to the probability of not a success, but the probability of a failure. This means the possible values of x are either having 0 successes out of like n trials, or 1 success, or 2 successes, or 3 successes, or 4 successes, or 5 successes, or ... n minus 2 successes, or n minus 1 success, or n successes in n trials. Those are the values that x assume. So x, again, is always assigned a numeric value that represents the number of successes that occur for a binomial experiment in n trials of that experiment. Using this notation, the binomial probability distribution function, okay, always computes the probability of having x successes in n trials. And ladies and gentlemen, welcome to the binomial probability distribution function. Here it is. Notice it makes use of our combination function. Okay, n in combination with x. N again is the number of trials in the experiment. X is the number of successes in n trials. P is the probability of having a success on any given trial. Q is the probability of having a failure on any given trial. Okay, that's called a binomial probability distribution function. Or as far as we are concerned with our TI-84, ladies and gentlemen, we call this the binomial or the binom PDF function or PDF. Binom PDF, we have a function on our calculator, our TI-84, that this stands for binomial probability distribution function. Or in some stats textbooks, they call it the binomial probability density function. Okay. Notice your combination function. This is how you compute combinations if you want to involve yourselves in the factorial function. We've seen this a long time ago. But ladies and gentlemen, we don't need to use this because we have the NCR function at our disposal. It hangs out in our probability menu. All right. So any questions about this function here? This is called the binomial probability distribution function. We are going to use this to compute probabilities for binomial experiments. All right. And I'm going to show you now where on the calculator that function hangs out. So I'm going to go get my TI-84 calculator. All right, if you hit your stat button, wrong. Clear that from your mind. Ladies and gentlemen, we got to go into our distribution mode. Above my VARS key, VARS key, I see DISTR. That's short for probability distributions. So to access our distributions mode, we have to hit our blue second key first, followed by the VARS key. That takes me into my probability distribution mode. I'm going to scroll down until I run into this fabulous function called the binom PDF. And there it is. That's your binomial probability distribution function. Built into this puppy here is this entire function. The entire thing is built in. You don't have to mess around with NCR or anything. It's all built into this one function, the binom PDF. So we'll be using that to compute binomial probabilities. Again, how did we access that again? We went into distribution mode. Second VARS, scroll down, and you'll run into the binom PDF function. All right. Does anybody in here not see that on your TI-84 calculator? Are we all able to access this function?
Yep.
And of course, this is assuming, ladies and gentlemen, that we all have a TI-84 calculator. If you don't have a TI-84 calculator, you're going to have to use a binomial probability table, which is at the back of your statistics textbook. It's in the appendix. In the old days, before the calculator, we had to use tables to look up various probabilities. But now we don't need that. The TI-84 has supplanted all the use of the tables. So much more convenient using the calculator now because it has a wealth of these functions built into it. All right, so we'll put that away for now. All right, here's an example. Suppose we have a die, a fair die, and we roll it 3 times. What is the probability that exactly 2 of the rolls are larger than 4? Well, now wait a minute, let's go. If we are going to try to model this according to a binomial experiment, can I allow my outcomes of rolling this die be rolling a 1 or a 2 or a 3 or a 4 or a 5 or a 6 or a 6? Is that possible to have 6 different outcomes? If I'm trying to model this according to a binomial experiment, it's not possible because a binomial experiment must only have what? 2 outcomes per trial. So therefore, okay, we can still entertain this question. We roll a die 3 times. What is the probability that exactly 2 of the rows will yield a face larger than 4? But this is how we're going to have to define our outcomes. We will have to define one outcome to be that we roll a face that is larger than 4. The other outcome will have to be defined to be that we roll a face that is not larger than 4. Wait a minute here. All right. Now, I have a question for you. What's wrong with these outcomes on this PowerPoint slide, ladies and gentlemen? There's a flaw in them. Look at this. Look at how they define the two outcomes. Larger than 4 or not larger than 4? What's the flaw? There's a typo here. There's an error.
Should it be including 4?
Yeah, what if we roll a 4? Where does a 4 fit into one of these outcomes? They have a little mistake here. They forgot about 4. No, what we should do here is we should define the one outcome to be that we roll a face larger than 4. That's one outcome. But the other outcomes should be that we roll what? A number that is
4 larger.
Okay, well, you know what? Actually, I said corrected. There is no typo here. Because to roll a face that is not larger than 4 says that we could actually roll a 4. Do you agree? A 4 or a 3 or a 2 or a 1. No, everything's okay. There's no typo on this PowerPoint slide. All right, false alarm. I apologize. All right, and the probability of each outcome is the same each trial. Yeah, that would be true because it's a fair die. And what happens on roll 5 does not care about what happened on the 4 previous rolls, et cetera, et cetera. All right, so all right, let's get back to this now. All right, we are counting the number of rolls larger than 4. So designate this outcome as being a success. So ladies and gentlemen, if I roll a die and its face is a number that's larger than 4, we call that a success. If I roll a die and its face is 4 or less than 4, we call that a failure. That's how we're going to define a success and failure for this experiment. Okay. Now, the only other possible rolls larger than 4 are 5 and 6. So, ladies and gentlemen, what's the probability of a success? What's the probability of rolling a face larger than 4? Well, that's equal to the probability of rolling a 5 or a 6. Do you agree? Which gives us a probability of what? 2 divided by what? 6 outcomes, 2/3, 2/6 rather, which is 1/3. So the probability of having a success for this experiment, the probability of rolling a face greater than 4 is going to be 1/3. And that occurs again if I roll a 5 or I roll a 6. A success will have occurred. However, what if I have a failure when I roll the die? Meaning, what if I roll a 1, a 2, a 3, or a 4? That's called a failure. And what's the probability of a failure? Well, that would be what? If I roll a 1, 2, 3, or 4, that would be 4 out of 6 chances of having a failure, correct? Because I could roll a 1, 2, 3, 4, or a 4. Or that is equal to 1 minus P, 1 minus 1/3, which is 2/3. So the probability of a failure is 2/3, and the probability of a success is 1/3. So there's a 33% chance, about a 33% chance that when I roll a die, I'll roll a face larger than 4. There's about a 67% chance that when I roll a die, I'll roll a face that is not larger than 4. Does that make sense there? All right, so now we can build our binomial probability distribution function. And in particular, ladies and gentlemen, we're interested in what? We're interested in computing the probability that exactly 2 of our 3 rolls are successes, meaning 2 of the 3 rolls will yield a face that's larger than 4. Now, here is a typo on the PowerPoint. They forgot to put what in for X. What should they have put in place of X here? They forgot to put what in? 2. Do you agree? we're interested in the probability of having two successes here. So they should have said P of 2. All right, so just P of 2. If you see P of 2, you know what that's saying? That's saying the same thing as the probability that X will be equal to 2. Remember, X is equal to the number of successes, okay, out of n trials of a binomial experiment. Well, the probability of having two successes, if you want to use this long, laborious formula, is going to be 3 in combination with 2 times the probability of a success raised to the second power times the probability of a failure, 2/3 raised to the n minus x power. 3 minus 2 power is the first power. You could go through all this factorial business here and get on your calculator and dial this up, and you get about 0.222. So according to this calculation, there's about a 22% chance that when I roll a fair die 3 times, there's a 22% chance that I will roll face larger than 4 on 2 of the 3 rolls. Okay. Well, there's an easier way to compute that probability. You don't have to involve yourself in the combination function or any of this other business here. All you gotta do is bring up your TI-84 calculator. Now, when we use this calculator here, we need to understand how to use the binom PDF function, okay? And actually, they're going to show us on subsequent slides here. So instead of me trying to write sloppily on these PowerPoints here, let's just move on here. Well, they don't show us. What the heck? Okay. No big deal. All right, so how can we do this on our calculator? Well, let's bring up our machine here. And I'm going to show you how to compute this binomial probability on your calculator now. All right. So we're going to ultimately be using the binom PDF function, okay, to compute this probability. And when we bring that binom PDF function up, we're going to need to know what the argument list requirement is, okay? Now, I think they do eventually show ourselves on this PowerPoint what that must be. Let's see here. Okay, here it is right here, Liz Owen. The function binom PDF requires this argument list, NPX. Let me see if I can highlight that so we can see like what it is I'm even looking at here, right here. Binom PDF function is going to enable us to compute this probability. The argument list requires n, the number of trials of a binomial experiment. P is the probability of a success. And X is the number of successes. NPX is the required argument list, and these have to be separated by commas. Notice that. All right, so therefore, let's go back. And let's show ourselves how to compute this probability using our calculator. So we go to distribution mode, second vars key. We don't go down and grab the binomial PDF. The number of trials we are conducting here is we're rolling this die 3 times. There's 3 trials in this binomial experiment. P is the probability of having a success. In this case, it's the probability of rolling a face that's larger than 4. We already computed that to be 1/3. X is the number of successes we wish to have in 3 trials, and we're interested in having exactly 2 successes. In other words, we're trying to compute the probability of rolling exactly 2 faces that are greater than 4 in 3 trials here. So X is assigned the value of 2 successes. This is what your binomial PDF function would look like if it was populated horizontally, because some TI-84 calculators don't give you that vertical way of looking at things or doing things on the previous screen. They'll just give you the function laid out horizontally, and you literally got to type in these numbers here: 3, 1/3, 2. Does anybody have a calculator out there that is horizontal as opposed to the previous screen, which was like vertical?
I do.
All right, it's no big deal. When you bring up the binomial PDF function, all you got to do is just remember to type in, it's got to be n, p, x. N is the number of trials, 3. And where's your comma button? Where is your comma? Well, your comma hangs out above your number 7 key. Do you see the comma button here above your number 7 key? Just make sure you separate the values of n, p, and x with commas, or else you will get a syntax error and the function will not perform. All right, so whether we got the horizontal nicety that my calculator has, or if you bring up the function and it lays it out horizontally with just an open parenthesis, you're going to have to type in 3, 1 divided by 3, 2, and then a closed parenthesis. Either way, hit enter, and ladies and gentlemen, there's our probability. So that's the probability of having exactly 2 successes out of 3 trials for this binomial experiment of rolling the die. Okay? Now we understand how we computed that much quicker than using the actual function, which requires the combination function, requires all this exponential, notation and stuff. This is so much more compact because it basically has all that built into the binomial PDF. You just got to remember the argument list, which is NPX. So again, this argument list is always going to be n, p, x. All right. That's the required argument list. Has to be in that order, and you have to have commas in between these. All right. That's good. Now we know how to use the binomial PDF function here. Okay. All right, let's move on here. All right, suppose we randomly survey 20 college students at a local college and ask whether or not they are statistics majors. The number of statistics majors at the college is fixed. So just like the playing card example, if you pick a statistics major for your sample, the probability that the next member of your sample is a statistic major decreases. So therefore, because it's kind of like an experiment without replacement, the members of the sample are not actually independent of each other. So the trials of choosing a student at random on this campus and getting one that's a stats major or not is not considered to be an experiment with replacement. Okay, so these are dependent trials, not independent. Now, this is a marvelous thing, though. If, however, ladies and gentlemen, the size of our sample is less than 5% of the size of our population, the change in probability is so slight, if we keep, a trial out of our lot and reach in and pull out another trial, that you may assume that the members of your sample are actually independent. And the probability of a success, finding the statistics major, basically would remain the same for all intents and purposes. In that case, under that assumption, we could then use the binomial probability distribution function to compute binomial probabilities. So what is this requirement again? Now, I got a question for you here. If this campus only had 40 students enrolled in it, very small college, ladies and gentlemen, and I randomly select 20 students and note whether they are a stats major or not, and keep that student out of the lot, and then reach in and pull out a second student randomly and note if they're a stats major or not, keep them out of the lot. Would the probability of selecting a stats major on any subsequent trials be affected by what's happened on the first, second, or third trials, etc.? In that case, if I only had 40 students, what's that? Do you think it would be affected? I'm sorry, I didn't hear you.
Yes, I do.
Yes, it would. It would be greatly affected if you only had 40 students and you're selecting 20, because like your sample size of 20 is much larger. I mean, it's much larger than 5% of the size of your population in that case. Okay. But listen to this question. If my college or university, let's say it's a fairly large university. Suppose we have like 50,000 students that attend the college, 50,000. And if I randomly select 20 students for my sample, despite me not putting the person back in and pulling out another person, despite having not conducted this experiment with replacement, would these subsequent trials still be in that situation? Would they be classified as being independent trials? If my sample size is 20, where my population size of the university is like, what did I say, 20,000 or 50,000? I forget what it was. So if I had 20,000, if we had 20,000 people attending this university, would a sample size of 20 be less than 5% of the size of the population in that case? Well, what would be 5% of 20,000? 0.05 times 20,000. Well, ladies and gentlemen, if I took 5% of all the students that attended this university, which I said is 20,000 students, is the size of my sample less than this? Is 20 the size of my sample less than this number here? The
Yes.
answer is yes, because 5% of 20,000, do it on a calculator, is 1,000. As long as I choose a sample smaller than size 1,000, ladies and gentlemen, we can consider these trials or these draws from the population to be independent of one another. If, however, I choose a sample that is like size 15,000, then those draws from the population will be dependent upon each other. Okay, so that's what this is trying to say. So this is very important here. If you're wondering or scratching your head, are these trials independent or dependent? Just remember this. If your sample size is no more than 5% of the size of your population, then you're okay. Those are considered to be independent trials. So it really depends, what size sample you're drawing versus the size of your population as to whether or not your trials are independent or dependent. But in this case, we will assume that our, university has many, 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 many students. And choosing a pithy size of 20 for our sample, we'll consider that to be less than 5% the size of our population. If that's the case, we can then use, with faith, and trust, the binomial probability distribution to compute probabilities. All right. And so, what was the question again here? Okay, suppose that 3% of the students at your college are statistics majors. So therefore, ladies and gentlemen, the probability of the success of me reaching into this population and randomly selecting a student, and the probability of me choosing a stats major would be about what? 3%. 3% chance. That's the probability of a success. What would be the probability of a failure then? Well, that's going to be 1 minus 0.03 or 1 minus p, which is q, which is 0.97. So the probability that I randomly select a student from my large population on this campus and I do not choose a stats major would be a 97% chance of a failure. Therefore, the probability that 2 people in my sample are statistics majors, In other words, the probability of having two successes. Okay, out of how many trials? How many trials were we conducting here? Two successes out of, oh, there were 20 trials, do you agree? We're selecting 20 students at random from our population. So the probability of having selected exactly two stats majors of the 20 students we randomly selected can be computed according to the binomial probability distribution. And they come up with a probability of 0.0988. So there's about a 10% chance that when I randomly reach into this population of all the students on this campus, that I select exactly two stats majors. There's about a 10% chance of that happening. Let's see if we can use our calculator now to compute this probability using our binomial PDF function. So bring up your calculator again. Clear your screen. Got to go get the binomial PDF function. How do we do that again? Oh, we got to go into our distribution mode. So second vars, go down, scroll down, and grab the binomial PDF function. There it is. Remember, the the required argument list for this function to perform properly is NPX. N is the number of trials, and there's 20 trials here. We're randomly selecting 20 students from the population on our campus. The probability of selecting a stats major is 0.03. And we're interested in having two successes. In other words, we're interested in selecting exactly two stats majors of the 20 randomly selected students from our population. Hit enter, and boom, there's your probability, 0.0988. And that's exactly what they computed using the long, laborious formula for the binomial distribution, okay? Are we computing these probabilities okay on our calculator with the binomial PDF? Are we understanding how this is working here?
Yep.
Okay, so I'm assuming that we're all good, unless you speak up. All right, let's move on here. Okay. What is the probability that at least one person in my sample is a statistics major? At least one person. At least one person. Well, ladies and gentlemen, the long way of computing this probability of having at least one person is to realize that this would be the probability they want us to compute. The probability that X is what? Greater than or equal to what? 1. Do you agree? Because that's saying at least one. Of having at least one success. Do you agree if I want to do this the long way, it's really going to be equal to the probability that I select one stats major or two stats majors or three stats majors or four stats majors or five stats majors or ... or 20 stats majors out of 20 trials. Can you imagine how long that's going to take on our calculator where we're going to have to bring up the binomial PDF function 20 different times? What a pain. There's got to be an easier way to compute this probability. Well, there is. The event at least one person in a sample as a stats major is the complement of the event of what? What's the complementary event of saying at least one stats major is selected of 20 that are selected randomly? The complementary event of at least one would be saying 1 minus the probability that X is what? Less than 1. Well, we cannot select a fractional or decimal number of students. And because of that, what's the next integer down from 1? What's the next integer down from 1? That would be 0. So this probability is equal to 1 minus the probability of having 0 successes, or X being equal to 0. So then instead of adding together 20 different probabilities and using our binomial PDF function 20 different times in our calculator, the easier way is to use the complementary probability rule. which is to say that it's just going to be 1 minus the probability of having what? No successes. In other words, 1 minus the probability of not selecting any stats majors of the 20 students that we randomly select. This is a typo. This should not be 2. What should this be?
0.
0. That is a blatant typo, ladies and gentlemen. That's got to be 0. So 1 minus the probability of 0 successes is equivalent to saying the probability that we have at least 1 success. And it's sure a heck of a lot easier going to be to do this than it is to what? To be adding all these together. So how do we do this on our calculator? Well, I'm going to show you now how we do this on the machine. We bring up our calculator. And all we got to do is clear our screen and type in 1, subtract. And now we got to go get the binom PDF function. So 1 minus second vars binom PDF. How many trials here? There's 20 students randomly selected from the population of students on the university campus. The probability of selecting randomly a stats major, we were told, was 0.03. And what do I type in for X? Remember, I typed in 1 minus. I want how many successes? 0. 1 minus P of 0, right? 1 minus the probability that X is equal to 0. We type in 0 here. And there you go. That's the probability we want to compute. This is equivalent to the probability that we select at least 1 stats major out of the 20 randomly selected. Hit enter, boom, you got your probability. So there you go, ladies and gentlemen. So there's about a 46% chance that when I randomly select 20 students from this university campus, there's about a 46% chance that I will select at least 1 stats major, at least. That's to say that I could select 1 stat major, or maybe I select 2, or maybe I select 3, or maybe I select 4, or 5, or 6, or 7, or 8, or 9, or 10, or 11, or 12, or 13, or 14, or 15, or 16, or 17, or 18, or 19, or all 20 that I select might be stats majors. Okay. We understand how the complementary probability rule came to the rescue here and prevented us from having to compute this laborious probability of adding 20 different probabilities together to satisfy the criteria of at least 1. Okay. So we should thank our lucky stars, ladies and gentlemen, that we have this complementary probability rule. Does that make sense? It helped us out here. Saved our butts. All right, here we go. This is just showing you how to use the binomial probability table to look up probabilities, which is in the appendix of your book. I'm not going to go over this. This table is in appendix A-2, the binomial probability table. This is the way we did things in the old days before we had the marvelous calculators. We had to resort to the tables to look up probabilities. You can look at this and, still, go back and look at the table and convince yourselves how to look up these probabilities manually. But ladies and gentlemen, we're going to use the binomial PDF function on the calculator. Take care of business. All right. Well, all right. Let's see here. Now, this is interesting. We've already learned that the binomial PDF function requires the n and the p and the x for the arguments. So to calculate the probability of exactly 5 successes out of 20, when the probability of success is 0.05, you would type, okay, binomial PDF 20, 0.05, 5. NPX. N is the number of trials, P is the probability of a success on any given trial, and X is the number of successes you're interested in. Check this out. This is interesting. You can also calculate several binomial probabilities at the same time. For example, if you type binomial PDF 20, 0.05, and inside braces 0, 1, 2, or 3, Well, you know what? They're also, I don't know, they're also, they left out a 4 here, ladies and gentlemen, comma 4. Because if you do that, closed brace, closed parenthesis, you will be able to compute the probabilities of having exactly 0 successes, 1 success, 2 success, 3 success, or 4 success here. Okay. I'm going to try something on the calculator. Let's try something radical. If we get in trouble, no big deal. We'll just clear the screen. Watch this. Suppose I have a binomial experiment where I'm going to conduct 20 trials, and the probability of a success in any given trial is 5%. Suppose I'm interested in building a list of probabilities for having exactly 0 successes, or 1 success, or 2 successes, or 3 or 4 successes out of 20 trials. Let's see if we can do this on our calculator here. So I'm going to try something out here. I'm going to try to even go above and beyond what this PowerPoint is saying here and show you something else. I'm going to go down and grab my binomial PDF here. 20 trials, probability of a success is 0.05, whatever the success is. We'll assume it's a binomial experiment of some kind. Now, what's going on here? Well, here, we're going to have to bring up the open brace. And where is the open brace? The open brace is above your open parenthesis key. So second open parenthesis brings up the open brace. And I'm going to type in 0, comma 1, comma 2, comma 3, comma 4. Closed brace is above your closed parenthesis. Second closed parenthesis. This is saying, ladies and gentlemen, I want this binomial PDF function to compute 5 different probabilities. The probability of having 0 successes, 1 success, 2 successes, 3 or 4 successes. But I want to tell my calculator, ladies and gentlemen, to store these successes in a list. So I'm going to say store, STO, off to the lower left of your keyboard. There's a button that says STO. That means store in list 1, second 1. Let's see if this is legal. I'm trying something. I don't know if it's going to work. Let's see. Oh, it looks like it did that. Tell you what, go to stat, edit, and there you go. Look at this. Ladies and gentlemen, what's the probability of having 0 successes out of 20 trials? 0.35849. What's the probability of having 1 success out of 20 trials? There it is. What's the probability of having 2 successes? There it is. What's the probability of having 3 successes? There it is. What's the probability of having 4 successes? There it is. That cool? Everybody follow what I just did there? Well, this is being recorded though. So you can go back and, you know, look at this and mull over this at any time of the day or night. That's the beautiful thing about this. All right, let's move on here. Okay. All right, just like we were able to find the mean and the standard deviation of any discrete probability distribution 2 days ago, well, guess what? The binomial distribution also has a mean and a variance and a standard deviation. And ladies and gentlemen, the mean of a binomial distribution is always equal to n times p. N times p. That's always the mean or the expected value of a random variable defined for a binomial experiment. N is the number of trials of the experiment. P is the probability of a success on any given trial. The variance of a binomial probability distribution is always n times p times q, which is to say n, the number of trials, times p, the probability of a success, times q, the probability of a failure. And if you take the positive square root of the standard deviation, of the variance, you generate the standard deviation of a binomial probability distribution, which is the positive square root of n times p times q. All right, so let's go back to our previous example. Remember rolling the die? We were interested in rolling a face larger than 4. All right, remember we rolled the die 3 times? What would be the mean for this binomial probability distribution? Well, there's 3 trials, n is 3, and the probability of success of rolling a face greater than 4 on any given roll, we computed way back, was 1/3. You know what the mean or the expected number of successes would be for this binomial experiment? It would be 3 times 1/3 or 1. So what's that saying? What it's saying is this. If we were to roll this die 3 times and keep track of the number of successes we had, in other words, the number of faces that came up larger than 4, if we were to do this experiment to say 100,000 times, if you added together all the number of successes of 3 trials of rolling this die, in other words, if you were to keep track and add together the total number of faces that came up greater than 4 and then divide by 100,000, you would come up with 1. Meaning on average, we would expect when we roll this die 3 times, on average, we would expect to have 1 success. We would expect to roll 1 face that's greater than 4. That's the mean or the expected value of the random variable for this particular binomial experiment of rolling the die. The variance can be computed as n times p times q, 3 times 1/3 times 2/3. P is the probability of a success, which is 1/3. Q is the probability of a failure of rolling a face that is 4 or less than 4, 2/3. The variance would be 2/3. Take the square root, and you got 0.816. So on average, if we roll this die 3 times, we would expect to roll 1, give or take, 0.816. We would expect of 3 trials of rolling this die, we would expect to have 1 minus 0.816 to 1 plus 8.816 number of those rolls come up with a face that is greater than 4. Okay? That's what we would expect. Okay. Does that make any sense? All right, let's go see if we can have a little bit of fun in the remaining time in our textbook. All right, let's go get our book here. And these problems will be coming out of section 5.3. Binomial distribution. That's what this section's entitled. As always, please do take some time outside of class to look down through these wonderful examples that your author does work out. I think that would be, to your advantage here. Let's see. Hold on a second. I want to take a look at some of these things here. All right, here's an interesting one. Let's look at example 5-20 here. Public opinion reported that 5% of Americans are afraid of being alone in a house at night. 5%. Are you afraid? If a random sample of 20, it seems like we're moving towards Halloween when you start watching these horror flicks, on TV. I don't know what it is, ladies and gentlemen, but it starts to create a lot of anxiety in your life when you are at home alone at night. So maybe it's good not to watch those horror flicks. All right, anyways, if a random sample of 20 Americans is selected, find these probabilities by using the binomial table, or we're going to use our what? Calculator. We're not going to use the table. What's the probability that of the 20 randomly selected Americans, what's the probability that exactly 5, are afraid of being alone at night? 5 people of the 20 that we randomly selected, what's the probability that all 5 of those, or what's the probability of having exactly 5 of our 20 that we randomly selected being afraid to be at home at night alone? Well, symbolically, that is having us compute the probability that X is equal to what? 5, correct? But they shorten this up in textbooks later on. They don't say this. They just say P of 5 with the understanding that we're interested in having 5 successes here. And you know what a success is defined to be for this problem? A success is defined to be that an American is afraid to be home alone at night. That's how we define a success for this particular experiment. All right, so how do we compute this probability? We use our binomial PDF function. So instead of using that table in the back of your book, we go get our binomial PDF. And what do I type in? How many trials are we conducting for this experiment? Well, how many Americans are we randomly selecting?
20.
So 20 is lowercase n. That's the number of trials. P is the probability of a success. In other words, what's the probability that any given American randomly selected will be afraid to be at home at night in their home? They told us it was 5%. 0.05 is the probability of a success. That goes in for P, 0.05. And we're interested in how many successes. We're interested in, the probability of having 5 of our 20 randomly selected Americans be afraid of being home at night alone in their house. So we're going to type in 5 here. That would be your X here. Okay. Dial it up on your calculator, ladies and gentlemen, to convince yourself that you get this probability. Are we all getting this probability here when using the binomial PDF function and dialing in 20, 0.05, 5?
Yes.
All right, there's your answer. So, the probability when we randomly select 20 Americans that exactly 5 of them are afraid to be at home at night alone is less than 1%. I mean, it's like 0.2 of what? 1%. Okay. All right, the second question. What's the probability that there are at most 3 people in our sample who are afraid of being home alone at night? At most 3. What does at most 3 mean? What inequality does that conjure up in your mind to say at most 3? We would say X is what to say at most 3 successes?
Less than or equal to 3?
That's right. X is less than or equal to 3 means at most 3, meaning the most it could be is 3, but that's also suggesting it could be something less than 3 also. All right, that means at most 3. What would at least 3 be? At least 3 would mean X is what? Less 3. Do you agree? Wait, did I say at least 3? Wrong. That's not right. No, to say at least 3, ladies and gentlemen, at least 3 would mean that X would be what? Greater than or equal to 3. That means at least 3. So this is at least 3. This is at most 3. What would it mean to say no more than 3? No more than 3. That would also mean what? X is less than or equal to 3. These are so important. I'm going to type this out here. So this would be saying at least 3. This one would be saying at most 3. Or, ladies and gentlemen, you could say no more what? No more than 3. That's what X less than or equal to 3 suggests. So at least 3 means greater than or equal to 3. At most 3 or no more than 3 means less than or equal to 3. It's important to know that, because if you don't know that, you're going to read these words and you're not going to know what inequality suggests here. Okay. All right. So here we go. Let's get back to where we were. All right. So how are we going to compute this probability using our calculator? Well, the complementary probability rule here really does not work. In fact, you would not want to use the complementary probability rule because the complementary probability rule, ladies and gentlemen, would be 1 minus the probability that what? What's the other side of the fence of saying X is less than or equal to 3?
Is 3.
Greater than 3. Do you agree? You don't want to use the complementary probability rule here. It's even nastier than the probability we're being asked to compute here. Because this would be saying 1 minus the probability that what? What's the next integer larger than 3? The next integer up from 3. Because you cannot have a decimal number of people or a fractional number of people. To say X is greater than 3, if it's to be an integer, is to say X would be greater than or equal to what? 4. But what does this mean? Could you imagine computing this probability? What this would mean is we would have to say 1 minus, we'd have to compute the probability of what? 4 successes plus the probability of 5 successes plus the probability of 6 successes. Oh, wait a minute. How many trials did I conduct here?
20.
20. What a hassle this is going to be. Do you agree? Plus dot, 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 all the way up to the probability of having 20 successes. What a hassle. You don't want to have to do this. This will take forever on your calculator. You're going to have to bring that binomial PDF function up 20 times. How many times there? 17 times. Do you agree? Isn't that true? You don't want to do this then. Too much work. Why not just compute the probability of being asked to compute in this case? The probability that we have what? At most 3. So yeah, you don't want to do this. Way too much work there. And so we'll just follow along with what happened in your textbook here. The easier way of doing this problem, to say at most 3, is to say that we could have 0 successes or 1 success or 2 successes or 3 successes. Believe you me, this is a lot more manageable than doing the complementary probability I just had up there. Yeah, you got to grab your binomial PDF function. How many times here? 1, 2, 3, 4 times. Do you agree? And that would take care of business. But I have an even more powerful function I can show you that'll even take the sting out of this altogether. But ladies and gentlemen, if you were to bring your binomial PDF function up 4 different times, each time letting n be 20 and a probability of success being 0.05, where your x would just have to change each time from 0 to 1 to 2 to 3, you would crank out these binomial probabilities. You add those together, you'd get 0.984. So there's about a 98% chance that when you randomly select 20 Americans, that at most 3 of them will be afraid to be at home alone at night. Okay. Everybody see that there? This is kind of a long way of doing things. But ladies and gentlemen, there's a quicker way. Oh, yes, there is a quicker way of doing this probability. And the quicker way is by using, you ready for this? There's another marvelous function built into our calculator. It is called the binom CDF function. This is CDF, not PDF. And this stands for binomial cumulative distribution function, where the argument list for this function is N, P, I like to say C. Where this is really equal to this probability, ladies and gentlemen, the probability that X is less than or equal to C. That's what this marvelous function does. It will always compute a probability like this, which is amazing, because here's what it's going to do behind the scenes for you. That one function is going to take care of all this business here. Because what it's going to do is it's going to add up the probability of having 0 successes to the probability of having 1 success. Add that to the probability of having 2 successes. Add that to the probability of having 3 successes. Plus, dot, on and on this goes, up to the probability of having C successes. This function is a lifesaver. It saves you a ton of time. Because to compute this probability, instead of having to compute 4 different binomial probabilities, 1 for each of these, 0 successes, 1, 2, and 3 successes. You know how we could compute this probability? It could have been computed a lot quicker had we just gone and grabbed our binom CDF function. So the binom CDF function, here's how we would populate its argument list here. Binom CDF, how many trials did we conduct? 20? What's the probability of a success on any given trial? 5%? 0.05? What's my number C? What's my number C here? What would be my number C? 3? I'm interested in at most 3 successes. Ladies and gentlemen, that's it. All you gotta do is bring this function up. Boom, it'll come up with your probability of 0.984. Let's go get that marvelous function and show ourselves how to use it on our calculator. So let's bring up the calculator. I'm going to now show you how to use the binomial CDF function. I got a question for you. When I bring this calculator up, are we seeing this red writing on top of the keyboard? Yes or no?
Yeah.
Yes.
Son of a gun. What a hassle. All right. Well, I'll tell you what. You don't need to see these keys down here anyways. Because look, I'm going to bring this up here. This little screen here. We go to our distribution mode, second vars key. You can see those keys. Go down and grab not the binom PDF, but the binom CDF. And there it is, right below the binom PDF function. Dial up that function. How many trials? 20 trials. That's N. P is the probability of a success, 0.05. Comma. We're interested in at most 3 successes here. Type in 3. Now, if you don't have it showing vertical like this to populate the argument list, if it pops up horizontal, you have to type in the argument list this away. Make sure you separate these numbers by commas. Hit enter, ladies and gentlemen, and watch this. Boom, done. 0.984. That saved a ton of time instead of having to use the binom PDF function 4 different times. Isn't that a marvelous time saver? That's called the binomial cumulative distribution function, or sometimes they call it the binomial cumulative density function. Depends upon what stat book you look at. All right, that's the binom CDF function. And again, that can only compute probabilities. They have to be of this form, though. The probability that X is less than or equal to some integer C. It has to be that type of a probability to be able to tap into this function. If it is, then you just populate the argument list as NPC. Boom. It'll compute the probability of having added up. Gosh, what? All these probabilities, computing them all individually and adding them up all at the same time. So this is a time saver. It saves you a ton of work. Okay. All right, I'm going to get rid of all this writing on here. We got to move on. So that's the binom CDF function. All right. Okay. Let's go down and see if we can have a little bit of fun now in our homework, our problems down here. Okay, skipping that, skipping that. Let's see, we probably have X successes. Okay. All right, ladies and gentlemen, for classwork number 2, I want you to do problem number 3A. 3A, use your calculator. Just use your calculator. This should not take a long time if we use our calculator. It should be a very simple problem. Go ahead. I'll give you 30 seconds to do this problem. 3A, using your calculator. Go ahead. That's all there is to it. Use your binomial PDF function. N is 3 trials. Probability of a success on any trial is 0.40. And we're interested in exactly 3 successes out of 3 trials. Boom, there's your probability. Did we all get that?
Yep.
All right, that's it. That's how you use your binomial PDF function. Notice the binomial PDF function only computes the probability for one specific number of successes. Binomial CDF not only computes the probability for several number of successes, different successes, but it also adds them together. Okay. All right, let's try another one here. Good, moving on. Okay, these are just more of the same. Let's see. All right, here we go, ladies and gentlemen. Number 7 here. Let's read this. It says, a survey finds that 20% of Americans suffer from a sleep disorder. For a randomly selected sample of size 20 people, find each of the probabilities. What's the probability that at least 2 people have a sleep disorder? At least 2 people have a sleep disorder. Go ahead and compute that probability using your calculator. What's the probability if I randomly select 20 Americans that at least 2 of them will suffer from a sleep disorder? Go ahead and compute that probability. I'm going to let you think about what's the most efficient way to do that probability. Go ahead. So which way are you going to compute it, ladies and gentlemen? Are you going to compute it the first way? Do I got any takers to compute it this first way here? This way? If you're going to do it this way, I'll see you later because it's going to take forever. Because you're going to have to add the probability of 2 successes or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11 or 12 or 13 or 14 or 15 or 16 or 17 or 18 or 19 or 20. That's going to take forever. No. Easier way. Use the complementary probability rule. This is equal to 1 minus the probability of the complementary event that x is less than 2, which means the next integer down is 1. This is the way to go. So therefore, you do it this way. So it's going to be 1 minus, well, what is this going to be? Hold on. Hold the show. Hold on. Okay. You agree this is gonna be equal to 1 minus the probability of 0 plus the probability of 1 success? Isn't that true? Or, ladies and gentlemen, I could use my what function? Since my probability looks like this. You can grab the binomial, what function?
Binomial cumulative function.
That's right, the binomial CDF function, even quicker. Even quicker. How many trials? How many Americans were randomly selected? There were 20. What's the probability of a success? A success is that they suffer from a sleep disorder. You see what I said about successes? They're not always good things. The success in this case is that we have a person that suffers from a sleep disorder. The probability of a success is 20%. They tell us that. And we're interested in at most how many successes? 1 success? There you go. That's all you got to do is dial this up in your calculator and boom, you've computed the probability that we select at least 2 people of 20 randomly selected that will suffer from a sleep disorder. So you gotta, at times use this complementary rule. It'll save you tons of time. All right, so let's go get our calculator and dial this up and see if we can bring that up properly there. All right, so here we go. I will try to compute this probability. So go, I got to type, hold on. I got to type in 1 minus first. 1 minus, now I go get the binomial what? CDF function. 20 trials. 0.20 is the probability of a success of selecting somebody that suffers from a sleep disorder. And I'm interested in 1. There you go. Boom. There's your probability. Anybody get that?
Yes.
So, ladies and gentlemen, there's a 93% chance that when I randomly select 20 Americans, there's a 98, what was it, 98%? I think, yeah, 98% chance that at least 2 of them will suffer from a sleep disorder. That's exactly what we just computed there. And there's, 93% chance. I'm sorry, I said 98. Was it 98%? I can't remember that. Was it 98% on the calculator or 93%?
93%.
It was 93%. My bad. Okay. Okay, let's see. So you just throw that as part of your classwork, that problem there. Let's see what else we got here. So is this binomial CDF function making sense? How it can save us some time here, coupled with maybe the complementary probability rule. Okay, he's 15 out of 20. Okay, all right, ladies and gentlemen, number 8. We'll roll this into a classwork here. See if you can do this one. Go ahead, try that one. I'm going to help you out a little bit here. Ladies and gentlemen, it's a 20-question multiple choice exam, and there's what, 5 choices, correct? Of the 5 choices for each question, how many choices are the correct choice?
1 out of 5.
1. So what's the probability of a success of guessing any one of these questions correctly? 1 out of 5, right? So what's the probability of a failure? That'll be 1 minus P, 1 minus 1/5, which is 4/5. So you got 4 out of 5 chances of not guessing one of these questions correct. And you got, or any question correct for that matter. And you got 1 out of 5 chances of correctly guessing any question. Okay, go ahead now that you're armed with that and see if you can do number 8 there. Okay, ladies and gentlemen, do you agree that the probability of guessing at least 15 of the 20 questions correctly is represented symbolically, that the probability that X is greater than or equal to 15? Do we understand it? Is that making sense? But do you agree to compute that probability, we would have to use the binomial PDF function once to compute the probability of having 15 successes or 16 or 17 or 18 or 19 or 20 successes and add all those probabilities together? What a hassle. Do you agree it's a lot easier to evoke the use of the complementary probability rule, which is saying this is equivalent to 1 minus the probability of the complementary event of saying X is greater than or equal to 15, which is saying X is less than 15. Oh, but what's the next integer down from 15? That's 14. So this is really equal to 1 minus the probability that X is no more than 14 of the 20 questions guessed correctly. Which now we can use the binomial CDF function. We bring it up. 1 minus binomial CDF, n is 20 trials. The probability of a success on any given trial, in other words, answering any question correctly, is 1 out of 5, comma, and C would be 15, what I called C. Bring it up on your calculator, ladies and gentlemen, and did we get this probability, which is very small?
Yep.
Yep.
I mean, that's a small probability. Geez, if you write that in what, decimal notation, do you agree we'd have to move that decimal point 7 places to the left? That's going to be like 0 point, there's going to be 6 zeros here. 1, 2, 3, 4, 5, 6. And then finally, we're going to hit the 1/8. Do you agree? That's a very small probability of guessing at least what, 15 of these 20 questions correctly. Is everybody understanding how we compute that probability using the binomial CDF function to save tons of time there? And the complementary probability rule. All right. So I think with these examples, ladies and gentlemen, that I've shown you, this is good enough now to propel you to success. I just want to show you one other quick thing here, if I could. Suppose that we had a binomial experiment where we have 5 trials. And let's suppose the probability of a success is 0.5 on any given trial. Are these trials fair, ladies and gentlemen? If I say the probability of a success is 0.5, are these fair trials? If the probability of a success is 0.5, that's called a fair trial. Do you agree 50-50 for a success or failure? All right, watch this now. I want to show you something here. What if I go get my binomial PDF function? You can just watch this. You don't have to do anything here. The number of trials I said is 5. The probability of success I said is 0.5. Now, watch this. I'm going to bring up my braces here. I'm going to type in 0 successes, 1 success, 2 success, 3 success, 4 success, or 5 successes. Close the brace. I'm going to store this in list 1. Let's go look at list 1 now. Ladies and gentlemen, I want to point something out very important here. Do you see symmetry? Is there symmetry with this discrete distribution, this binomial distribution? This is 0. This is 1, 2 successes, 3 successes, 4 successes, 5 successes. Think about graphing this, using your bars. Remember I showed you that, how you can graph a discrete distribution? Is this a symmetric distribution? Just look at these numbers here. Do you agree that 0 success probability corresponds with 5 success probability? You agree 1 success probability corresponds with 4 success probability? Do you agree that 2 success probability corresponds exactly with 3 success probability? Ladies and gentlemen, this is a perfectly symmetric binomial discrete probability distribution. You see that there? And you know why it's symmetric? Because what did I say was the probability of a success? What did I say? It was 0.5, which means each trial is a fair trial. That's why we have a symmetric distribution. If we have 5 trials And we look at the probabilities of a 0, 1, 2, 3, 4, or 5 successes. We have a perfect symmetric distribution. I just wanted to point that out to you. All right, you guys have a good weekend. I will open up the quiz on chapter, what is it? 5, do you agree? Wait a minute, let me look at the schedule again one more time here. Chapter 5 quiz is opening up, correct? We just completed chapter 5.3 homework. The chapter 5 homework is due on October what? 21st, midnight. The quiz is due by midnight, October 21st. Okay, those dates are aligned. I just want to make sure those dates were aligned there. All right, so there you go, ladies and gentlemen. You have a good day. I'll stay on the line. If you have any other lingering questions